In this video, I'll be teaching you guys about inductors. So what does an inductor look like inside of a circuit? Simply the squiggly line. If you've learned about transformers already, it's the same thing but just without parallel curly lines. Now the thing about inductors is, well, they look exactly how they look like in real life and also in the circuits. They're just simply coils of wires. Alright, so inductors, they store electric energy in magnetic fields. Now, this right here isn't too important, alright? Especially when you're taking a circuit analysis class. You're not really going to care about this detail. Maybe in electromagnetism class, you're going to care a little more, like physics 2 usually. But right now, I'm teaching circuit analysis. So I'm not going to cover too much about the physics behind this, especially since I haven't learned it yet. When I take my electromagnetism class, I will make that playlist. But, okay, inductors. What is the variable you're often going to see for inductors? L. Alright, L, V of L, voltage at inductor, I of L, current at inductor. L, your variable for inductance. Okay, so inductance, the variable you're going to see in formulas for inductance is L. Alright, but what's the unit for inductance? Well, the unit for inductance, so unit, is Henries. Henries, or also just abbreviated as H. So if you want to say something had 3 Henries, you write down 3H. All right. So remember, Henries measures inductance, sort of like how centimeters measures height. Okay. So in this case, the analogy would be height would be your inductance in this analogy, and centimeters would be your Henries in this analogy. So just keep that in mind. All right, how do you calculate, what's the formula for inductance, right? Especially when you have a time-dependent system, which is just something called alternating current. So this is in AC. So in order to calculate voltage at an inductor, you simply multiply your inductance by the derivative with respect to time of your current at the inductor, and then you can find the voltage at the inductor. So remember, just take the derivative of your current. So let's say IL of t at this inductor was equal to, let's say at this inductor it was equal to 5 cosine of t. All right, amps. Well, if you just simply take the derivative of this, then you would get d of dt for I of L would be equal to negative 5 sine of t amps, correct? This is the derivative of the formula above. And let's say the inductance was, I don't know, 5 Henries. Okay, so you simply multiply 5 by the derivative of your current. So 5 times this, these two multiplied together, is equal to negative 25 sine of t volts. My bad. This unit is not amps. This unit would technically be amps over time, but I'll just leave it. I'll just leave it empty. Okay. So basically, the formula is pretty self-explanatory. You just take the derivative of your current and multiply it by the inductance. Now you could reverse this around, so you have to use integrals for this in this case. But for this entire series, for as long as I'm going to be covering inductors, I'm not going to make you take any integrals or anything like that. I'm just going to worry about derivatives. All right. So let's go ahead and move on to some very simple problems so that you can learn how to use this formula for inductance. So what we have right here is a pretty simple circuit. There's just a singular inductor with a voltage, and you are given the current at this voltage source in milliamps. All right, keep that in mind. Milliamps is important. Now, you can't really solve more with your current knowledge. For most of you guys, you won't be able to really solve circuits with capacitors and inductors together. You're going to require either differential equations or learning how to use the phasor domain, which is a way easier way that's just only comprised of algebra and a little bit of trigonometry. But yeah, we're not going to worry about that too now. We're just going to solve very simple circuits in this video. So we have a current. So if we use KCL, since this is an entire series circuit, right, everything is end to end, that means this current is also equal to this current, right? So 3 sine of 5t milliamps is equal to IL of t. Okay? All right, now that you have this, what do you do? Well, you can simply use the inductor formula. Let's use our more space that we have. So our inductor formula says that the voltage at an inductor is equal to the inductance times the derivative with respect to time of your current. So I should put VL of t here. So VL of t. Okay, this is the formula. So if we substitute everything in that we know that the inductance is 3 Henries. And what's the derivative of your current? Well, the derivative of your current is the derivative of this guy. So if we use some chain rule, we just simply bring out the 5 and take the derivative of sine. Bringing out the 5 just gets 3 times 5. What gets 15 times the cosine of 5t milliamps per second, I guess, right? But I'll just omit the units because that doesn't really matter too much. Now we got this, right? Just 3 times 15 to get 45 cosine of 5t volts for the voltage at your inductor. So 45 cosine of 5t volts is here. Well, if you do a little bit KVL, actually, you'll realize that your voltage at your source should be equal to the voltage at the inductor. So this voltage here is just equal to 45 cosine of 5t volts. Let's go ahead and solve this circuit. So you're given the current. Basically, if we just use KCL, since this is a series circuit, so KCL series, then all the currents should be equal to each other. So I of S is equal to I of R, which is all equal to this current right here. 10 sine of 3t amps. Okay, once we get this, we simply need to find V of L. So if we use the inductor formula, the formula for voltage of an inductor, V of L is equal to inductance times the derivative with respect to time for your current. You get, what do you get? So 5 Henries times the derivative of your current, which is this, which is 30 cosine of 3t. And all this equals to what I write amps. All this equals to 150 cosine of 3t volts. So this right here is your voltage at your inductor. All right, let's do one more step. We can use Ohm's law at this resistor, correct? So we have the current and we also have the resistance. So 1 kilo ohm times the current, 10 sine of 3t amps. So you can get, well, you would simply just get 10 sine of 3t kilovolts. So this right here would be the voltage at your resistor. Now, what's the last thing? Well, we have I of S, I of R, and your I of L. So we have all the currents, and we also have the voltages at the resistor and the inductor. We don't have the voltage of the voltage source. So let's go ahead and use KVL to determine this. So KVL, in the counterclockwise direction, let's say, has two voltage rises, your VL and your VR. And in turn, this equals VS, correct? Okay, so all we need to do is add VL and VR together to get your voltage at your voltage source. So 150 cosine of 3t plus 10 sine of 3t kilovolts technically. This would be 10,000 then. Okay, let's put 10,000 here to turn this into kilovolts. 10,000 volts is equal to the voltage of your voltage source. So this right here is the function that represents the voltage of your voltage source by simply adding the two functions of your voltages at your inductor and at your resistor. But essentially what I'm just showing you is how to use the new derivative formula, the new calculus formula that you just learned. But overall, everything's still the same. Ohm's law, KVL, KCL. So, as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.